What if everything you know about mountains is incomplete? The Himalayas, the Andes, the great continental ranges that have defined human imagination for thousands of years. We have named them, mapped them, and climbed them. We believe we know where Earth's grandest terrain lies. We are wrong. The longest mountain system on this planet is not on land. It does not appear on any travel map. No one has ever stood at its peaks, watched the sun rise over its ridges, or felt the wind move across its slopes. Because where it exists, there is no wind, there is no sunlight. There is only pressure, darkness, and cold, and a silence so complete it has lasted for millions of years. Stretching more than 65,000 kilometers beneath the surface of the world's oceans, the mid-ocean ridge system winds continuously around the entire planet. A single, connected chain of volcanic mountains so vast it could wrap around Earth nearly twice. Some of its peaks rise higher than the Alps, measured from their base. Others are still growing right now, built slowly, from molten rock pushing up through the seafloor. And almost none of it has ever been seen. This is not a gap in an old map waiting to be filled. It is one of the largest unexplored landscapes in the known universe, and it is right here, on the planet we call home. Which leaves a question worth sitting with. If the greatest mountain range on Earth has been hidden beneath the ocean this entire time, what else have we been standing directly above and never thought to look for? For most of human history, we assumed the deep ocean floor was featureless, a vast, lightless plain of mud and silence. Nothing dramatic, nothing worth looking for. That assumption held for centuries. It took a war to break it. During the Second World War, naval ships used sonar to hunt submarines. The method was simple. Send sound downward, wait for the echo, measure the distance. But the echoes kept returning wrong, not from a flat bottom, but from slopes, ridges, shapes that had no business being there. After the war, scientists turned those same instruments toward curiosity. By the 1950s, mapping confirmed something extraordinary. A massive mountain chain running through the center of the Atlantic Ocean. Then surveys expanded into other basins, the Indian Ocean, the Pacific, the Southern Ocean. Every time, the same structure appeared. Not separate features, not isolated ridges. One continuous system, a single mountain range connecting every ocean on Earth. The scale was almost difficult to accept. But what mattered most was not the size. It was the question these mountains immediately raised. Why are they here, still growing, in the one place on Earth we never thought to look? These mountains exist because the ocean floor is not permanent. It is being created right now, continuously, without pause. Along the crests of mid-ocean ridges, tectonic plates slowly pull apart. The movement is almost imperceptible, a few centimeters each year. Roughly the speed at which fingernails grow. Nothing that could be felt or noticed in a single human lifetime. But deep beneath, something far less quiet is happening. As the plates separate, pressure in the mantle drops. Solid rock begins to melt. Magma rises through fractures and meets near-freezing seawater, cooling almost instantly into new crust. New seafloor, new terrain added to the planet's surface every single day. This process has been running for hundreds of millions of years. The Atlantic Ocean continues to widen because of it. North America and Europe are still drifting apart slowly enough to feel nothing, fast enough to reshape the world over geological time. And that leads to something worth pausing on. Much of the seafloor beneath us today did not exist when dinosaurs walked the Earth. The deep ocean is not ancient, unchanging landscape. It is some of the youngest terrain on the planet, constantly born, constantly renewed, built fresh from the inside out. The most surprising discovery along these mountains was not geological, it was biological. In 1977, scientists exploring a mid-ocean ridge near the Galapagos found something that quietly dismantled one of biology's oldest assumptions. At depths where no sunlight had ever reached, where pressure was crushing and temperatures extreme, they found life. Not traces of it, not scattered microbes. Dense, thriving ecosystems. Hydrothermal vents on the seafloor were releasing superheated water packed with dissolved minerals. Temperatures exceeding 350 degrees Celsius, yet the water remained liquid under immense pressure. And surrounding these vents, entire communities had built themselves around that energy. Giant tube worms stretching over 2 meters, blind shrimp navigating by heat, bacteria converting toxic chemicals directly into energy through chemosynthesis, no photosynthesis, no sunlight required. A complete food web, built entirely in the dark. This forced a fundamental question. If life does not actually need sunlight, if it only needs energy in some form, then everything we assumed about where life can exist may be too narrow, too Earth's surface, too familiar. Because if ecosystems can flourish in permanent darkness at the bottom of our own ocean, the universe suddenly has far more places worth looking. Despite decades of study, we still know remarkably little about these mountains. Consider this. We have more detailed maps of the surface of Mars than we do of our own ocean floor. A planet tens of millions of kilometers away has been charted with greater precision than the terrain directly beneath our ships. Only about a quarter of the seafloor has been mapped in high resolution. The obstacle is not indifference. It is physics. Ships must move slowly across vast distances, pulsing sonar downward, building maps one narrow strip at a time. Satellites help, but they only resolve large shapes. Fine details stay buried, hidden behind kilometers of water that no signal can fully penetrate. Estimates suggest more than 100,000 seamounts taller than 1 kilometer may exist across the world's oceans. Most have never been directly observed. Some likely host ecosystems found nowhere else on Earth. And that leaves science in an uncomfortable position. We do not know how many species live on these mountains. We do not know how many ecosystems exist in that darkness. We do not know what is down there. For a species that has split the atom, landed on the moon, and mapped the human genome, that is a remarkable thing to admit. The largest unexplored environment on Earth is not somewhere distant. It is beneath us. These mountains do not simply exist beneath the ocean. They shape it. When deep currents encounter seamounts, they are deflected upward, forcing cold, nutrient-rich water toward the surface in a process called upwelling. What happens above is remarkable. In ocean regions that would otherwise be nearly empty, life concentrates. Fish gather in numbers. Corals take hold in the cold darkness far below. Seamounts become oases. And the life found there operates on timescales that are difficult to fully absorb. Some deep-sea corals growing on these underwater slopes began their lives thousands of years before the first pyramids were constructed. They were ancient before human civilization had a written language. They are still growing today. But that slowness comes with a cost. In the deep ocean, everything moves at a different pace. Growth is slow, recovery is slower. Damage that takes seconds, a trawling net dragged across the seafloor, a single destructive pass can erase structures that required centuries to form. These mountains may appear to be bare rock. They are not. They are foundations of some of the most fragile ecosystems on Earth, systems that function across timescales. No single human life can fully witness, quietly sustaining ocean health in ways we are only beginning to understand. These mountains hold something else entirely unexpected, a record. As molten basalt rises and cools along ocean ridges, tiny magnetic minerals inside the rock do something remarkable. They align themselves with Earth's magnetic field at the moment of solidification, locked in place forever, a precise timestamp written into stone. Over millions of years, Earth's magnetic poles have reversed repeatedly. North becomes south, south becomes north. And each time it happens, newly formed crust captures that reversal, preserving it as a distinct magnetic stripe on the seafloor. The result is a pattern of alternating bands radiating outward from both sides of every mid-ocean ridge, like barcodes written into the planet itself. When scientists first mapped these stripes in the 1960s, the symmetry was undeniable. Identical patterns on both sides of the ridge, mirrored perfectly exactly what would be expected if the seafloor was continuously spreading outward from the center. It was the evidence that finally confirmed plate tectonics. From these magnetic records, scientists reconstructed how continents drifted, how ancient oceans opened and closed, how supercontinents broke apart across hundreds of millions of years. The mountains beneath the ocean are not just terrain. They are the planet's own archive, quietly preserving the full history of how Earth became what it is. Not all underwater mountains follow the ridges. Some rise alone, isolated giants emerging from the flat abyssal plains, thousands of kilometers from the nearest plate boundary, and among them, one stands above all others. Mauna Kea, in Hawaii, is commonly listed as the world's tallest mountain when measured correctly, not from sea level, but from its base on the ocean floor to its summit above the clouds. That true height exceeds 10 kilometers, taller than Everest, yet most of it remains submerged, invisible, unknown to anyone who has not looked beneath the surface. Chains of similar volcanoes stretch across the Pacific, each one marking the slow passage of a tectonic plate over a fixed hotspot deep in the mantle. Older volcanoes, younger volcanoes, a timeline of movement stretching back tens of millions of years, written in stone across the ocean floor. But some seamounts tell a stranger story still. Certain flat-topped underwater mountains called guyats were once islands. Their summits were leveled by waves under open sky. Then, as the crust beneath them gradually cooled and subsided, they sank, slowly, completely. What is now deep ocean was once coastline, places where sunlight reached the seafloor, where waves broke against volcanic rock under an open sky, now buried under kilometers of darkness and silence. Exploring these mountains is among the greatest challenges science has ever faced. The obstacles are not political or financial, they are physical. At typical ridge depths, pressure exceeds 300 times that at sea level. Temperatures hover near freezing. No sunlight has touched these slopes in millions of years. The environment is hostile in ways that are difficult to overstate, and reaching it requires technology pushed to its absolute limits. Modern robotic vehicles have changed what is possible. Remotely operated machines now descend where humans rarely can, mapping terrain with extraordinary precision, capturing footage of lava formations, fault lines, and biological communities never previously seen. Yet progress remains slow against the scale of what remains unknown. More humans have walked on the moon than have visited the deepest sections of these mountain systems. That comparison is not poetry. It is simply true. And still, every descent returns with something unexpected, a species unknown to science, a geological formation that rewrites a textbook, a community of organisms thriving in conditions that should, by every prior assumption, be incompatible with life. The deeper we go, the more clearly one truth emerges. The deep ocean is not a dead place waiting to be cataloged. It is an active, living, continuously surprising world, and we have barely opened the door. When we imagine mountains, we picture sky, peaks cutting through clouds, wind, cold, thin air, the feeling of standing above the world and seeing everything below stretch outward to the horizon. But most of Earth's mountains know none of that. They rise in permanent darkness, beneath kilometers of water, in silence that has never once been broken by wind or weather or the presence of anything human. No seasons reach them, no sunlight has ever touched their slopes. Yet they are not still, not passive, not simply rock waiting in the dark. They guide ocean currents. They shelter ecosystems built across timescales longer than civilization itself. They regulate ocean chemistry, influence carbon cycles, and support food webs that ultimately connect to every living thing on the surface above. They are not separate from our world. They are part of what makes our world possible. And perhaps the most humbling realization after centuries of exploration, after satellites and submersibles and all the instruments of modern science, is how little we still understand about the largest landscape on our own planet. We have not reached the end of discovery. We have barely found the beginning. The deep ocean is not empty. It is not silent. It is waiting patient, vast, and full of answers to questions we have not yet thought to ask.